A compiler is a software tool that helps us as a bridge between human-readable code and machine code. This way, the machine can read and execute our code. This compilation process has 6 steps. The first 3 are front-end, the last 3 are back-end, and also 2 other parts that are very important in each of the steps: the symbol table and the error handling. Let's start with the lexical analysis. The purpose of this is to break down the source code into tokens. Tokens could be separators, operators, keywords, identifiers. And it will be each one of these parts of the code converted into a sequence of tokens. Let's say we have string C equals A plus B. In this case, the token string would be: a string is a keyword, C is an identifier, equal is an operator, A is an identifier plus an operator, B an identifier, and the semicolon a separator. The first step also eliminates our comments and the white spaces. Once we have the perfect code, we need to validate our grammatical structure. This happens in our second step, our syntax analysis. We will take this equation and we will create a tree in which we could see the operators and the identifiers in a hierarchical structure. And now, having this and having no mistakes or errors, we will follow to the next step.
The third phase is called the semantic analysis phase. In this phase, the compiler ensures that the code makes sense logically. It looks for the correct meaning in a program by checking types, scopes, function calls, and logical consistency. If an error occurs during this phase, then the compiler will not proceed with the code generation. It basically takes the syntax tree produced in the syntax analysis phase and it verifies its correctness and meaning and produces the semantically verified parse tree, which is used later on in the next phase. When we are checking the tree, we look for errors in type checking, undeclared functions and variables,
scope errors, function call errors, return statements, array indexing, division by zero, incompatible assignments, break and continue statements inside of loops, errors in multiple declaration of variables, struct and class members access,
and implicit type conversion. Basically, there are 2 types of semantics: static and dynamic. The static is the one that is checked during the compilation phase, and the dynamic is the one that is checked during runtime. Now, in the third phase of the example that we've been using, we take the syntax tree and we start with type checking. We check that hola and mundo are valid strings and that the IDs or variables A, B, and C are of type string. Later, we do an operator resolution, which verifies that the plus sign is a valid operator for strings, which in Java is a valid operator for concatenation of strings. Finally, we do a scope resolution, which ensures that the variables that are concatenated, A and B, have been properly declared. The fourth phase is called the intermediate code generation. In this phase, the compiler will convert the source code into an intermediate machine-independent representation, also known as IR, which lies between a high-level source code and a final machine code. It is not specific to a particular machine, making it portable and easier to optimize. So basically, the front end translates the source code into an IR, and then that IR is used later to generate the target code. So it's basically translation, portability, and optimization. Because of the IR code, portability will be enhanced. So for example, if a compiler translates the source code into the target machine code without using the intermediate representation, then for each new machine, a full native compiler and a new optimizer will be required. Meanwhile, if you have the IR, you'll only need one, with making it easier to apply source code modifications to improve the performance of the source code. Now, some common intermediate representations are LLVM, used by Clang, Rust, and Swift; Java bytecode, used by Java, Kotlin, and Scala; Microsoft Intermediate Language, used by C#, F#; and WebAssembly, used for running multiple languages in browser. Now, some types. Low-level IRs, such as TAC and SSA; high-level IRs, such as AST and CFG; and platform-specific IRs, which are LLVM, Java bytecode, and WebAssembly. I'll explain to you one of them, TAC, or tree address code. Basically, a tree address statement involves maximum 3 references consisting of 2 operands and 1 result. It doesn't need to be 3, but it can maximum be 3. A sequence of 3 address statements collectively forms a tree address code, which is typically X equals Y of Z. Now, for the example, we will use the 3 address code that will represent the concatenation as an abstract operation that at runtime will combine A and B. Now, T1 will equal hola, T2 will equal mundo, T3 will equal T1 plus T2. So basically, C is T3, A is T2, and B is T1. If we had, for example, the expression X equals A plus B times C, then T1 will be C, T2 will be C times B, T3 will be A plus T2, and now T3 will be T2.
By now we have already analyzed a lot of our code. We have made it into tokens. We look for possible errors while syntax or even the logic makes sense, and even make it more optimized by the intermediate code generation, the previous step that Sofia was talking about. Holy shit, there's a fly. So now we're gonna try to even make it more optimized before compiling. You might be asking already, why are we going to optimize it even more? Well, all of us want our code to run as fast as possible and as little demanding in resource as possible. So let me tell you how we do it. Previously, Sofia told us that we have a T1 value that's been already created, that is A plus B, hola mundo. Hola mundo already exists in the T1 variable, so we're going to assign it to C. When we assign it, we're going to delete the T1. So now we don't have A plus B, we only have C, a simple variable. We're only declaring the string, and that's the optimized version. We're no longer doing A plus B equals C. We're now simply telling that C exists and is hola mundo. Now that we have our most optimized as possible code that is going to be A equal hola, B equal mundo, and C equal hola mundo, not as a concatenation but as a string in itself, we can create our corresponding bytecode that will eventually send to the JVM in order to run our code. So in other cases that we have to concatenate an even larger, more complex with different type of data, or even calling from objects, we might have to use string builders or even more methods. So this compilation will be way longer. But as our code was simple, the most simple way was simply declaring 3 variables as locals, and that's it. That's how we came from A plus B to simply make it as simple as a single variable. That's the end of the video. Hope you like it, and yeah, see you in class.